Good evening, everyone. I'm Todd Borison. I'm the director of Las Cumbres Observatory, and it's my great pleasure to introduce you tonight to a so far unique event, the beginning of multi-messenger astronomy, which some of which took place right here in Santa Barbara. Las Cumbres Observatory is a nonprofit observatory. We're headquartered in Goleta. We've built and we operate 20 telescopes all around the world at currently 6, but soon to be 8 astronomical sites. We've built our observatory with the idea of studying things that change, and so having them distributed around the world allows us to observe them continuously, and that, in this case, turned out to be a very good thing. We've operated for 3.5 years now, and we have a long, bright future ahead of us. The observatory itself is the vision of Wayne Rosing. Wayne is an engineer and technologist who worked at Apple, Sun, and Google, and a lot of the technology that you use every day, he led the teams that created that. And so we're honored tonight to have him here to introduce Iair for the talk.
Thank you, Todd. Thank you, Todd. Las Cumbres Observatory, well, one of the questions I always get is, what is this Las Cumbres thing? It's supposed to be La Cumbre, isn't it? Well, it turns out there's a community, it's a commune, effectively, of about 100 families who own collectively 1,200 acres west of Los Gatos in the southern Bay Area. And it's called Las Cumbres Conservation Cooperative. And it's kind of a not quite correct Spanish, meaning the summits or the mountaintops. And we were on a mountain ridge, and so that's how Las Cumbres happened. And in basically 1984, 83, 84, it occurred to me when I was still working at Apple that the internet was going to happen, personal computers were going to happen, software that's accessible to people was going to happen, and digital camera technology, otherwise known as CCDs, was going to happen. And all of a sudden, it was possible to build observatories of small robotic telescopes that could go all around the world. And I thought, that's a neat idea. And after a few years, I decided, well, we'll found a nonprofit and we'll figure out how to go do this, and this will be my retirement project. And that was back in about, what, Dorothy, 86 when I started speaking that way? So that's about right. So we're looking at a project that's gone on in my head, at least, for over 30 years. And in 2005, came here full time, and we started on Haley Street in a little rented place next to the packing place there. I think that there's a wine place, LCO, and a packing place. I'm not sure there's a plan in that, but that's where we started and had lots of tacos across the street while we were building this thing, getting it started. So this started in Santa Barbara, and what's really thrilling is, now that we've been running, we had this absolutely amazing discovery that we were involved in. It could be the biggest and most important scientific discovery our observatory will ever really be participating in, although you'll hear tonight, it's expected that we'll be doing this pretty regularly. So without further ado, I would just want to thank the team for what they did. They delivered on the vision, we built it, and the science team delivered it. And so thank you. So many of the scientists are here tonight. None of this is done by one person, but tonight you'll hear from Dr. Iair Arcavi, who was one of the principal people in Andy Howell. Andy's right here, stand up, Andy. Andy's the staff astronomer who started our supernova project, and out of that, postdocs came in, and you'll hear about what happened. So without further ado, where's our speaker? There he is.
Thank you very much. About 130 million years ago, in a distant galaxy, 2 neutron stars spiraled in, generating gravitational waves as they got closer and closer together, and eventually merged, producing an explosion of material and light. The gravitational waves and the light, hot on their heels, traveled across the universe for 130 million years and arrived here on Earth in the early morning hours of August 17th, just under 3 months ago. For the first time in the history of this planet, we were ready for them. That day was a very busy day and will be remembered in the history of science for several reasons. It was the first ever detection of gravitational waves from merging neutron stars. It was the strongest, closest, and best localized gravitational wave event we have ever seen. It was the first detection of light and gravitational waves from the same event. It was the first time we ever saw something we call a kilonova. And it was the first time we were able to pinpoint the galaxy from which gravitational waves event came. We didn't sleep for 2 months after this day. So if you don't quite know what all of this means, you're in the right place, because this is what we want to tell you about today. So I'm very excited to share with you this discovery that is really a once-in-a-lifetime event for many of us. And we're so glad to see that you came here and that you want to hear about it and are interested in it. So this starts actually about 100 years ago, of course, with Einstein, who in 1915 came up with a beautiful theory to explain gravity. We all feel gravity intuitively. We know that if we hold something out and drop it, it will fall to the Earth because of Earth's gravity. We know that the moon rotates around the Earth because of the same laws of gravity, and the Earth around the sun, and so on. But Einstein was the one who really explained what actually is gravity. How does the Earth know that the sun is there and that it needs to revolve around it in the exact way that it does? And the idea is so elegant that we actually have a demonstration here for you about how this works. So we're going to show it to you over here, and we're going to try, and let's see how we do this. We're going to try and show you what's going on. So if you can, let's turn that, let's see here. So you need to, no, hang on. Is it? Yeah, okay. So this is so that we can show you what's going to happen here. Okay, so this is Griffin here, a graduate student at UCSB at the observatory. He's holding this iPad, so you can all see yourselves over there. Okay, we're going to walk over here to this demonstration. So this was kindly provided to us by the Santa Barbara City College Astronomy Club, so thank you very much. Okay, so Einstein's very elegant idea was that space itself can be stretched and curved like this sheet of spandex. Now, space is not an actual material, but the idea being that actual distances between 2 points can be made to shift and curve. Let's see here. Oh, I left my neutron star over here. Here we are. So the idea in its basis is very simple. It says that mass curves space. So empty space will just be flat, but if you have mass, it will curve space. And then another mass just sitting there, doesn't need to know gravity or anything. It just follows curved space and falls onto the bigger mass. Gravity is essentially, according to Einstein, the curvature of space caused by one mass. Okay, and if the mass is not falling, if it has some movement, it can orbit the other mass. Okay, so this is how planets orbit stars. Don't be worried by the fact that our planet is slowly spiraling into its star. This is one of the limitations of a demo like this, which has friction, but in space we don't have friction, so that's one of the differences. But the idea is the same. And of course, if you have two massive objects, you can now get them to orbit each other. Let's see if I can get this to work here. One second. Okay, this is harder than it looks. Okay, we saw them spiraling in a little bit. Okay, thanks. So that is the idea of how gravity works according to Einstein. So the idea is summarized in these very elegant sentences that people have used to summarize. This, by the way, is the general theory of relativity. Mass tells space how to curve. Space tells mass how to move. This is the essential part of it. Now, the idea is very elegant, but it is all rooted in math. So there are equations that describe exactly what is going on, in the real space, and how gravity works it. There are quite a bit of equations to do that. Don't worry about them too much. There will not be a quiz at the end, but just to show you that we can actually calculate very precisely what this means. And this is very important. It's not just an idea, philosophical idea, mass curves space. There are actual calculations, and they explain the physical world very accurately. 1 year after coming up with that theory, Einstein took the next big step, took his idea one step further, and said, well, if space is flexible enough to curve, maybe it's flexible enough to wiggle and warp and ripple like waves do. And now these gravitational waves, which are actually distortions in space, are not distortions of any material, but of space itself, were a prediction that just came out of the math. And we can't cause these ripples just by moving, our hands around or something like that. You can, but they'll be very weak. Really, you need some very high energy astrophysical process like the merger of two neutron stars to make this happen. Now the question is, can we measure this? How do we measure this, space itself being distorted? And the idea actually, or the instrument that actually is being used, was invented by this man, Albert Michelson, in the late 1800s. He was a very famous experimentalist, built some of the most precise instruments of his time. He was the first American to win a Nobel Prize in the sciences. He was famous for measuring the speed of light, and later actually running an experiment that was crucial for Einstein's earlier special theory of relativity. The instrument he made, which he's showing here, is called the Michelson interferometer. Here's how that works. It's a pretty simple instrument in its basis. You have a light source. You shine a light at a beam splitter. The light gets split in two, hits two mirrors, comes back, reunites with itself, and hits a detector. Does not sound so, incredibly innovative to do this, but it actually really is, and here's the reason why. Light is a wave, and anything that is a wave will interfere. So what does that mean? If you have two waves that are synchronized with each other like this, and you add them up, you get a stronger wave. So the peak meets the peak, and the valley meets the valley, and they strengthen each other. But you can do a really cool trick with waves, is that if you shift one a little bit and then add them, now a peak meets a valley, and they cancel. This is a pretty revolutionary thing. It's called destructive or constructive interference. Think about it for a second. Anything that's a wave can cancel itself. So sound is a wave. This is actually how noise-canceling headphones work. They generate a sound that's just shifted in phase from what you want to cancel, and it just annihilates it. So you hear about it in sound. This also happens with light. Here is how it works in the interferometer. So here's the same thing I showed you before, but a little bit more 3D here, is the wave of one light hitting one of the mirrors, coming back, and this one is set up so that it meets up with the other wave in exactly the opposite phase, and they cancel. So for example, you can get them to cancel. So you have light and light making darkness. That is a very unintuitive concept. And because it's unintuitive, we actually want to show you here how that works. So we actually have a Michelson interferometer here on stage, and we're going to show you a bit of this right now. So let's see if we can get our camera going again. So this is a very delicate instrument. Here we are. So we have it right here. See if Griffin can show you that this is a laser right over here. So it'll shine the light. Here is the beam splitter, which will split it in two perpendicular directions. And it hits these two mirrors, come back, reunite, goes through this hole, and it'll enter this screen we have in the box over here. So we're going to turn the laser on, and hopefully we can get the lights a little bit dim so we can see it. Let's see here. Yep, okay. So if Griffin can zoom in on that, I want to show you something. Let's see. Okay. Can you all see the stripes of darkness and light? Those stripes of darkness are where light is meeting the other light from the other path in an opposite phase and canceling. I'll prove it to you by blocking one of the light paths. You see it's all illuminated. I am adding a path of light, and that is creating dark bands where there was light before. So by adding another option of where light can go, it is making bright spots darker. Okay, so this is light and light making darkness. And then it's in stripes because in some places they meet and in this constructive interference, and in some places destructive. I'll block off the other path just so you believe me. Just regular light bouncing off a mirror and coming back, but when I allow it to meet light from another path, instead of always making it stronger, in some bands it makes it weaker and cancels, and you get a dark band. Okay, thank you, Griffin. So that is the idea of the Michelson interferometer. What does this have to do with gravitational waves? Okay, here is what a gravitational wave looks like when it's propagating through space. Now this is very hard to visualize because gravitational waves are three-dimensional. If actually there are four, but let's not go there. So this is like showing you a slice of what it looks like when a gravitational wave moves through space. It is actually moving, this is actually happening in all directions, but you couldn't see it if it were just all on top of each other. The idea is there's a gravitational wave moving forward from here, so space is being distorted. So if I'm standing here, you'll notice that in this direction, distances are getting longer and shorter, and in this direction, they're doing the same thing, but in an opposite phase. So one direction is getting squeezed while the other direction is getting stretched. And this is space itself stretching. So these distances are getting closer together and then further apart, and the opposite is happening in the perpendicular direction. This is how gravitational waves propagate. The problem is if I would just hold a ruler, my ruler would shrink and expand. Just with space, I would not see anything. Okay, that's why it's a very tricky measurement. But the Michelson interferometer can tell. So imagine a gravitational wave is now hitting this interferometer head on. It'll make one of the arms shorter and one longer, changing the relative phase of the waves of the light as they meet at the other end. So by one getting shorter and one getting longer, this relative phase changes, and then you get the constructive or destructive interference depending on the wave that's passing through. And in fact, the frequency that this changes is exactly the frequency of that wave passing through. And it is such a delicate instrument because you just need to move it by the wavelength of the light. And the wavelength of the light is a very small number. So that's how you can actually use this to measure very, very accurate distances. Now, the gravitational waves, even from merging neutron stars, which we'll get to in a second, coming from a distant galaxy, by the time they get here are very, very weak. So the fraction of how much each of these arms is going to change when a gravitational wave from a galaxy, say 100 million light years away, passes through it, is pretty small. There should be 21 zeros there if I wrote it correctly. So the actual distance that the arms are going to change is the length, the full length of the arms times that number. Okay, so you want to make your interferometer really big. Okay, if a gravitational wave were to pass through our Michelson interferometer, you have to take the length of the arms here, which is like 4 inches, multiply by that, and try and measure that. Okay, that will be very hard. So what they did is they built a really big Michelson interferometer. That is what LIGO is, the Laser Interferometer Gravitational Wave Observatory. It's essentially the same thing we have here, just much bigger. Each of these arms is about 2.5 miles long. So you have light bouncing off a mirror that way and this way and meeting here and making destructive or constructive interference depending on if a gravitational wave is passing through that or not. Now, this is such an accurate measurement, even with 2.5 mile long arms, the change that happens when a gravitational wave passes through it is about 1/1000th the size of an atom. This is the most precise instrument ever built. It can measure displacements of 1/1000th the diameter of an atom, or a distance called an attometer. And sorry, I should say it's not 1/1000th the diameter of an atom. It's 1/1000th the diameter of an atomic nucleus, which, okay, at this point, you know, it's already very small, but even smaller than that. Now, because this is such a sensitive measurement, they built 2 of them. So one in Louisiana and one in Washington State, so that they know if a gravitational wave passes, they will detect it in both of them, and that will confirm the signal. And the other reason is by the time difference between when the gravitational wave hits Louisiana and Washington, you can tell the direction of where it came in the sky. It's a very small time difference. Gravitational waves move at the speed of light, but it's measurable. So here are some of us at one of these sites, at the Louisiana site. You can see that tube is where the laser goes, one of the arms of the interferometer, and you can't even see where it ends. And in fact, at those lengths, you have to take into account the curvature of the Earth. If they didn't, the laser beam would hit 3 feet above the mirror on the other side. So this actually was probably the most precise concrete pouring and leveling ever undertaken. Here is the mirror at the end of one of the tubes. You see, kind of like ours, a little bigger. And here is their beam splitter with a very excited technician. Again, very same, just show you it's the same idea. The light gets, that's where it gets split into the 2 arms. Just everything is bigger and, of course, much more precise. Because if you're measuring things that precise, any little noise can cause you to get a signal. When we're visiting the control room of this thing, I saw a screen where they monitor the sloshing of the ocean, which they can detect in their instrument, both the Pacific and the Atlantic. It is very sensitive. So this is quite an incredible feat of engineering, and it turned on for the first time in its current form in September of 2015, and immediately they found the first gravitational wave, and that made a lot of news because it was the first time we were able to detect essentially waves of gravity. coming from space. It not only confirmed Einstein's theory from 100 years ago, but it also meant we now have a totally new window on the universe. The first thing they detected was the merger of two black holes. Black holes are the most massive, dense objects in the universe. Therefore, they make the strongest gravitational waves when they merge together. Unfortunately, that's all they do. They are black. And so those of us with telescopes cannot see anything. It's only the gravitational waves that we can detect, and we only know which direction they came from. If we want to study these systems more precisely, we need something that emits light as well. And this is where neutron stars come in, the second densest and most massive objects in the universe. Neutron stars are the leftover remnants of massive stars when they collapse and explode. These things have about the mass of the sun, but a radius of a city. So they're about 10 miles across, but they pack in the mass of an entire sun. It's basically, they're called neutron stars because most of the particles in it are neutrons that are pushed in so densely together. So it's not even normal matter as we're used to it. Atoms don't exist anymore. You've squeezed things so hard, all of this mass into this tiny region. It's essentially like one giant city-sized atomic nucleus. So you can think of it as a city-sized star or a city-sized atomic nucleus. Either way, it's quite an impressive object. And we see them in the universe. And occasionally they happen in pairs. And when they do, they can spiral in each other and merge. This is a simulation of two neutron stars merging, and you'll see it's quite a messy process. Much more messier than we had in the demo over there. Material is flying out, and this is great because that is something we can see. Unlike black holes where nothing can escape, from neutron stars, material can fly out and be heated and generate light. And this material actually has so many neutrons in it and is so hot that it is the only way we know, or one of the main ways we know, to create the heavy elements we see around us that are very neutron-rich elements. We can only think the universe can only make them in explosions like this or in mergers like this. So here's what we think happens when two neutron stars merge. So this is an illustration. And here are the two neutron stars just at the moment of merging, right there in the center. There's stuff flying out. The first thing, of course, that happens is they emit gravitational waves. You can see that depicted in these kind of like waves in the grid here. So there's a lot of mass moving very fast, and it shakes with space-time like this, and those are gravitational waves that are then detected by the LIGO detector. But they also create all of this material that flies out, and this is material where neutrons are squeezed into atoms at very high temperatures and very quickly. A neutron left alone will, within about 15 minutes, turn into a proton. And that is no good if you want to make elements that have a lot of neutrons in it. Once it gets into the nucleus of the atoms, it'll stay a neutron. So you need to get it in there quick. This is what we call the rapid process of nucleosynthesis, or R process, which you may have heard of in some of the news articles about this. So this happens very quickly. These neutrons are squeezed into nuclei of atoms and make the heavy elements, one of which is gold, which we know exists, but weren't sure where it was made in the universe. And as they do so, they also get very hot and emit light. And this light is what we call a kilonova, because it's predicted to be about 1,000 times brighter than something else that we call a nova. It's not related, but that's how the name came about. It's 1,000 times brighter, call it a kilonova. Another thing you'll notice here is these jets of material. So in the polar regions of these two neutron stars, when they merge, they will emit a very high energy jet of just very fast moving material that is so hot it emits in very high energy called gamma rays. This is in fact the highest energy light. And that will emit light for about 2 seconds in what we call a gamma ray burst. But you only see it if you're looking from the right direction. So you have to be in that, that jet of particles has to be facing you for you to see it. So we've seen gamma ray bursts before when neutron stars merge, or we thought that's what was happening, and the jet was pointed at us. We see a gamma ray burst for 2 seconds, and then that's it. When the jet is pointing at you, it's so bright that's the only thing you can see, really. But we didn't know until now if that was really what was happening, if they were really coming from merging neutron stars. So the idea was wait for LIGO to detect a gravitational wave, then we know to turn our telescopes, and even if that jet is not pointed at us, we should see the light from this gold being created in the kilonova. The problem is, with two detectors, really what you get is just a rough direction on the sky. This is what it looked like in September when they discovered the first merger of two black holes. They give us this Aiir region on the sky, which the technical term of which is an Aiir banana, which you can see why. And it's a huge part of the sky. And they essentially, this is essentially them saying it happened somewhere here, probably. Okay, it's not even 100%, it's like 90 something. That's very hard to find a little faint, burst of light that might last only a few days. A kilonova supposed to fade away after a few days if you don't know exactly where to look. So the expectations were that this kilonova, which people said should happen when you make all this gold and other materials, will be faint. Okay, it's 1,000 times brighter than nova. That's still pretty faint when you put it far away. It should be pretty much, kind of red or even beyond red, what we call infrared. Those were the predictions. And it will be somewhere in a large part of the sky that we won't be able to tell you exactly where. So any sensible astronomer wanting to find these things should obviously use a large telescope so you can see faint things, an infrared camera so you can catch where most of the light is expected to come out, and a field of view for that camera that covers a large portion of the sky. Right, very sensible way to go. What we had was small telescopes with visible light cameras that cover a tiny percentage of the sky. So we kind of came to this as the underdogs of this endeavor. And so I was a little, I was hoping, but it was a kind of surprise when I got the email from Todd Borison, our director, saying, I'm pleased to tell you that your proposal for searching for optical counterparts to gravitational waves has been granted time on our network, because initially it was not the best fit for what we want to do. However, we do have an advantage that no one else has, and that is that our observatory is not really one observatory. It's 20 telescopes at 6 sites around the world, and they are all fully robotically controlled. No one is running these telescopes. They are completely autonomous. They are controlled by software, and software is much more dynamic and flexible than people are. It does not have to fly to these places. It just transmits over the internet. And so this global network of robotic telescopes is unique in astronomy. There is no other thing like it. No one else has it, and it's run right here from Goleta. So we figured we should have, yes? We figured this should give us some sort of advantage, right? Okay, but how do you get over the problem that the Aiir bananas are really big and our field of view is really small? This is to scale a real event that happened by LIGO. It said, okay, here's a map of the sky. It happened somewhere in there. That's the size that you get to see in each picture you take. How do you find the needle in a haystack? So here's where you have to be a little bit clever. Mass in the universe, stuff in the universe, is not just evenly spread, in space or in this Aiir banana. It's in galaxies. Our sun is part of the Milky Way galaxy, together with another 100 billion stars. And the next big galaxy over is about 2 million light years away. So if a neutron star merger happened here, and some alien civilization from a distant galaxy were looking for it, there's not much point in looking between the empty space between us and the next galaxy. They should probably just look at the galaxy, so we thought we should do the same. And our camera can capture an entire galaxy in its field of view. They're smaller than these circles. That's just to illustrate where they are. And what we need to do is figure out what are the most likely galaxies, what's the most important ones to observe, hit those, and hope we catch where the kilonova is. By the way, this specific map over here was from not a gravitational wave event, it turned out later. It was from someone plowing snow next to one of the LIGO detectors. I told you these things were sensitive. Someone was plowing snow, it looked like a gravitational wave signal, we observed 50 galaxies, and then a few days later it was like, oh, sorry, it was just this guy plowing snow. Okay, so that's part of the deal, you're playing with when you have these kinds of sensitive instruments. But we were ready for it. We wanted it to happen. We set up this whole system where they send us an alert. We have a computer listening for it. It figures out which galaxies to observe at what priority, and then sends that to the telescope. And this can all happen automatically without any of us involved in a matter of seconds. We did put in this web page so that we can see here the galaxies it selected. Is a list of like 30 galaxies, goes down further. These are just the first 5. It's selected for us on August 17th. And we just have to click that big green button that says send to a telescope. And we're hoping in the future we don't even have to do that. We just trusted enough to let it go. At least that was the plan. Here's what actually happened on August 17th. So if you remember when two stars merge, you can look at the gravitational wave they make. As the stars get closer and closer, the gravitational waves get stronger and stronger and closer to each other, so the frequency goes up. You notice that? It gets stronger and higher frequency. Here it is again. So what you're expecting is you're expecting to see when these gravitational waves arrive at Earth, you see some waves going up and down, and then they're going up and down faster and stronger, and then it stops. Here is the signal that the LIGO detector in Hanford, Washington saw. So you're going to see this is time going to the right and frequency going up. So here's the signal. You see a strong, this is all noise, but you see a strong signal over here going higher and higher frequencies, higher and higher frequency. It gets really high and it stops. That is exactly what the merger of two stars looks like in gravitational waves. Takes a few seconds, frequency gets higher and higher, and that's where they merged. So that is exactly what they were looking for. That is one detector. Here's what the other detector saw in Louisiana. That is not a real thing. That is a glitch in the detector. It's kind of like a popping sound you might get on your audio system. It's just an electronic glitch that happens. It's less than a second long, so they were never worried about it, because what's the chance that a glitch would happen exactly when a gravitational wave arrives, right? Of course, you can see the gravitational wave detection right here behind it in this detector, but because there was a glitch, the automatic software said, I'm not dealing with this. I'm cutting this part out, and you only have that to work with. So initially, there was only, very strong detection. This is the strongest one ever. But we don't have a position because we only have one detector. Okay, so there's data to be rescued from there, but in the meantime, we don't know where to point our telescopes. Okay, miraculously, or not miraculously, but just amazingly, at the same time, the NASA Fermi satellite, which is detecting gamma rays. So this is basically a gamma ray telescope in space. Lucky for us, the atmosphere shields us from gamma rays, which are very dangerous. So we send satellites into space to see gamma rays, and this satellite sees gamma rays all the time. But on that particular day, it detected a burst of gamma rays exactly 2 seconds after that gravitational wave signal. Here's what it looked like combining the two. So you'll see the gravitational wave signal I showed you before from LIGO, and you'll see the readings from the Fermi satellite up there. And so this is just background level, but here is the stars are merging and merging, and the gravitational wave is getting higher and higher frequency. And then 2 seconds later, there's a hit. This had not ever happened before, and it is not a chance coincidence. It's not exactly that it's not a chance coincidence. The probability of it being a chance coincidence was calculated, and it's 5/1,000,000%. Okay, there's a 5/1,000,000% chance that this gamma ray burst just happened to happen 2 seconds after this and is not related to it at all. Okay, so the working theory was that these two things are related. The other weird thing, though, is that gamma ray burst was about 100 times fainter than any gamma ray burst we've seen before. So that was weird. The other thing I want you to notice is the frequency of the gravitational waves. This is how many times space-time is moving up and down per second. So 100 or 300 times per second. That's actually pretty close to middle C in sound. This is not sound waves, these are waves of space-time, but if they were sound waves, I can show you what they would sound like. Apparently, gamma ray bursts sound like the default Microsoft chime. But that's, okay, that's the animation they produce. That's what we have to work with. So that is actually the actual frequency of the gravitational waves translated into sound. So when this happened, even though it was just one detector of LIGO instead of two, but there was also the gamma ray burst at the same time, this is when things really got crazy. So the first thing that happens is they send out a circular, which is the, I saw someone call it the astronomical equivalent of a bat signal, except it looks like it was typed on a typewriter, but that's how it comes in email. And you'll see here it says the onboard trigger of the Fermi blah, blah, at this time is approximately 2 seconds after the single LIGO trigger reported in this earlier circular. Okay, that, people immediately understood this is very unlikely to be by chance. It's very important. This is a merger of two neutron stars, and we got the gamma ray burst. We were lucky enough that it was pointed in our direction. No one expected that to happen. While they were working on this other detection from the second LIGO detector for us to get a position, we had the position from the Fermi satellite. So this gamma ray burst satellite can also give a position on the sky of where the gamma ray burst came from. It's just even worse than the LIGO position in that it's huge. This is another map of the sky, and that is the region where they said it could be. So this is an accurate depiction of where they said it could be in the sky. It's most likely here, but it could also be here, it could also be here. And this is we were all of our software, everything we had prepared was ready to accept the LIGO localizations, those error bananas that came in a specific format that we knew how to read. And now suddenly this localization from the satellite is something completely different that, of course, we don't know how to read. So here's an accurate decryption of our reaction to that. There's clearly something very important going on. Time is of the essence, and this is not how we had planned it to happen. So we immediately started observing, we had to manually do what we had planned the software to do for us, which is find what galaxies are in here and start observing them. And we did that. We started observing galaxies in the center of this region, sent that to our telescopes. Our telescopes started taking pictures of those galaxies, and we started looking at them. Finally, 5 hours later, they were able to remove that glitch from the data. So they said here, investigation of the Livingston data identified noise, which is a known glitch during the in-spiral signal, and we were able to remove it with all these methods, whatever, and an app-dated sky map is available from all 3 gravitational wave observatories. You notice all 3 because that is the 2 LIGO ones in Washington and Louisiana, and a third detector in Italy, which had turned on 2 weeks before. This detector is called Virgo. It's a little bit smaller than LIGO. It's just 2-mile-long interferometer arm, so it's a little less sensitive, but it had switched on 2 weeks before. So together, now that you have 3 detectors, you can get a much smaller region of the sky where it happened. And finally, they put that data together, were able to remove that glitch and said, okay, it's somewhere in here. Okay, so again, a depiction of our reaction is that, because we were observing all the galaxies in the center, right? That was the highest probability region. We just did what made more sense. But now we have to stop observing all of those, it's not there, and start observing a whole set of galaxies over here. So lucky for us, our telescopes are very obedient for now. They do what we tell them. So we told them, stop that, forget about those galaxies. Here's a new list of galaxies. Now our software worked perfectly. It identified the galaxies, prioritized them, sent them to the telescopes, and the telescopes immediately start observing these galaxies for us. Those are the actual 4 first galaxies on our list that we observed. Here's a full position of all the galaxies. There's a full moon, just to give you a sense of the size of this on the sky. So again, we can't, even with this region, which is smaller than it was, because we now have the Italian Virgo detector, it's still pretty big. So we have to look at the different galaxies. And on the 5th galaxy on our list, was a galaxy called NGC 4993. And that little point of light you see over there is the Kilonova. Thank you. Okay, so how do we know that's a kilonova? It's pretty bright, and you can even see it's pretty blue, which is not what people told us to expect. Well, the first clue was that it wasn't there before. Here's an image from an archival image of that galaxy. Here's the image we took that night. That is not there. It's new. Okay, so that is clearly interesting. And then we later found out that there were 5 other observing groups, 5 other teams that were also looking at that galaxy, and we all took these images within 42 minutes of each other. And these are 6 teams that are all using different telescopes, using different techniques, using different lists of galaxies. Some of them are just tiling the whole region because they have the big telescope with a wide field of view. Some of them are like us, and they're searching galaxies, and they had a completely different way of doing it, and we all converged on this galaxy within 42 minutes of each other and all saw that new source of light. And this is when the reports started flying. And we notified everyone there's something there you should look at. NASA's SWIFT satellite was pointed at that to look at UV and X-rays. Of course, the Hubble Space Telescope was pointed there as well. In fact, about 70 observatories were looking at this. Observatories on every continent, yes, every continent, including Antarctica, were looking at this object in every single wavelength of light that we have. This is pretty much every professional-grade telescope on the planet, plus every professional-grade telescope off the planet as well. So 7 different space telescopes were looking at this. But the telescopes on the ground had a big disadvantage because this part of the sky was visible for only an hour and a half after sunset. It was setting in the western sky because it was close to the sun. You could only see it for an hour and a half. So everyone had to get their observations and then sit around and wait for 23 hours to get their observations again. And this, in the meantime, this thing was changing. It was evolving. It was changing very fast. We wanted to get as much information as possible. So I'm going to let Andy here explain how we get around that problem at Las Cumbres.
Getting around that limitation is exactly why we built Las Cumbres Observatory.
With the help of some very special effects.
Telescopes placed all around the globe so that there are always telescopes in the dark. These icons represent where we have telescopes. When we first discovered the explosion, it was over Chile. But then, as the Earth rotated, we picked it up again over Australia. And then, 8 hours later, we saw it over South Africa. In the 24 hours that the Earth takes to rotate, we can observe the explosion 3 times with our network.
So having telescopes around the world turned out to be the most important thing you could do to follow this event. So here's what we got. Here is our image from this is what the brightness of this was, and the first image we took, okay, this is about 150 million times as bright as the sun. Remember, this one was 130 million light years away. That is actually our kind of galactic neighborhood in astronomical terms. So our first image put it there. We were then able to take another image as the Earth rotated a few hours later in Australia, and it had already gotten brighter. Our next image taken in South Africa showed it had gotten much fainter, and it continued to fade and drop like a rock from there. So we had never seen anything this bright fade this rapidly or change color this rapidly. It went from blue to red in just a few days. We'd never seen that before. So we knew we had something here that was different than what we'd seen before and was related to the gravitational waves and the gamma ray burst that was seen. And we were the only ones capable of getting a data set like this. Think about it. If you only have a telescope in Chile, the next data point you're going to get is this one. It's just going to look like it's going down to you. We were I think to this day, the only ones able to get this rise and decline, which is going to prove later very important for constraining what we think happened here. So these very rapid changes in the first day are going to actually be able to distinguish between different theoretical models of what we think is happening in the kilonova. So our data set was a part of many. This is one paper that came out just showing you a timeline, starting with the gravitational wave. You see the signal there you saw before, the gamma ray burst, and then the optical data from the 6 teams, including us, that got there first. And then just all of these lines are those circulars of people sending circulars to each other. Oh, I observed it here. It looks like this. I observed it here. It looks like that. Just going crazy. And then there are also X-ray. Was detected in the X-rays a week later and was detected in radio waves a week after that. And this was actually quite a mystery. Why did it turn on in the radio and X-rays a week after we saw it in optical light? And we actually don't yet fully know the answer to that, but we can combine all of this data together and try to figure out what happened. So I should tell you, this is one of 80 papers that came out the day that this was released. This specific one has 3,500 authors on it. It combines all of the optical, radio, infrared, UV, X-ray, gamma ray, and gravitational wave data from the day of the discovery. That's why there are so many people. We were one of them. I was one of the people assigned to coordinate this paper, and can tell you the telecons we had were as fascinating as the discovery itself. So here's what we think happened. This is the simulation I showed you before. The neutron stars merged together. They started generating gravitational waves that were detected 130 million years later by LIGO. As they merged together, they launched a jet pretty much in our direction. And then all of this material came out. You saw there was like this blue flare, which is what we think we saw in the first days. And then the rest of the material is going to give out this red light later on. So let's go back to the slide I showed you before and see if this now makes a little more sense. The first ever detection of gravitational waves from merging neutron stars, the strongest, closest, and best localized thanks to LIGO, Virgo turning on 2 weeks before, gravitational wave event. The first time we saw light and gravitational waves from the same source. These are two totally different ways of studying the universe, one of which was only available for us starting 2 years ago, and now we can combine them. First ever detection of a kilonova, that brightening of the light because of all the materials that are created, and the first time we could pinpoint which galaxy it came from and tell the distance and exactly where it came from. So what did we learn from that? We learned a lot of things from this one event. Maybe one of the important ones is the following. So the event had to be kept a secret. This is how LIGO works. They want to be really sure that it's real and not, you know, some person plowing snow before releasing it to the public. Because if, you know, they cry out kilonova every time and it turns out to be a person plowing snow, it'll be very bad for them. So they want to be really sure. So, you know, but we really want to know where to point our telescopes immediately. We can't wait for them to be sure. So we had to sign an agreement with them that if we want to know where to point the telescopes, we have to keep quiet until they're ready to announce it. So we reluctantly did. So we had to keep this a secret. Everyone on the observing teams who was following this had to sign an agreement ahead of time with them to keep it all a secret for those 2 months. Except we're not really good at keeping secrets in astronomy. So this is a tweet that came out from Professor Craig Wheeler at the University of Austin, University of Texas at Austin. Look at this is a one day after new LIGO source with optical counterpart. Okay, should say he was not part of the agreement. He heard about it somehow, which I'm sure people are investigating. And then tweeted, he later apologized, and you know, okay, I should have let LIGO release when they wanted to, but the tweet was out already. Now, if you happen to have missed that, the Hubble Space Telescope, in fact, all of NASA's telescopes, tell you the information of what those telescopes are looking at is public. Of course, no one bothers to go into the logs and look at them, but they made a website which says, you know, called Space Telescope Live. What is Hubble looking at now? And one of the people who had triggered Hubble had the brilliant idea of calling his target BNS merger, which stands for binary neutron star merger. You know, you tell it to point somewhere, you give it coordinates, you have to give it a name. It's part of the form you have to fill out. So he said, sure, BNS merger. It's a binary neutron star merger. Put that in the name. You know, the logs automatically, this is a website, it's just automatically updated, gives you that information. Now, okay, who's looking at Space Telescope Live website? Okay, no one knows about it. So they make sure you do by also tweeting it. So this appeared on Twitter, the exact same thing. I'm looking at a star in all caps, BNS merger with Space Telescope for this person, Matt Nickel, who was the one who triggered the telescope for that observation. So this was all automatically set, right? They had never thought to turn this off for this event. At this point, it was getting a little hard to hide, and some online news articles already came out about, okay, we may have detected a new kind of gravitational wave. These are the rumors swelling over that. This was already coming out already early September, actually, even before August was over. Then, if that wasn't enough, we got this email a few weeks later telling us we were notified by one of the here that we accidentally made publicly available all the circulars. These are all those telegrams I showed you before, the bat signals we send to each other, for 2 hours. So all of our internal communications of here's what I saw, here's where it is on the sky, here's how bright it is, all the information was online for 2 hours before they took it off. And then, of course, a day before the final announcement that we were all going to say it'll finally be public and we don't have to worry about this, the transient name server, which is the thing we use to give names to different transients, sent out an email to their entire email list. Here's a transient called 2017 GFO. It's the name we give it. It's right at this position. It was discovered at this day. And it has a, this is how bright it was. And oh, it's a kilonova. Sent to everyone. So, I think the moral here is astronomers really cannot keep a secret, intentionally or not intentionally, which I think is great, because next time you hear someone, with their conspiracy theory about what astronomers or NASA is hiding from them, just remind them how this went down. Thank you for the compliment that we would be that organized to have a conspiracy, but just not clearly proven that doesn't work. Okay, but what did we actually learn scientifically? So one of the most important things we learned is by watching this kilonova, we can figure out what elements were made there. Here is the periodic table with all of the elements that are powered by a kilonova. Now we know. We did not know this 2 months ago, 3 months ago. We didn't know, we thought these things should come from merging neutron stars. That's the only thing we knew that had the right conditions to make the majority of these elements. And now we've actually proven that. We've seen these elements created in the right amounts to explain all of the abundances of these elements we see in the universe. So most famous, of course, and made the news, gold is made in a kilonova. So if you have a gold ring or a golden necklace, look at it for a second. The atoms in that necklace were made in the merger of two neutron stars. That is the only place gold can be made in the universe. If you trace back the atoms in your gold jewelry, they will come, you'll trace them back to being forged in the merger of two neutron stars. Same thing for silver, iridium, lead, most of these other heavy elements that we had not known where they came from before. So the golden Iair wedding band was made by a kilonova that happened, so long time ago, somewhere here. That material gets flung out into space and eventually made the sun, and leftovers of it made the Earth, and that's how the gold got deposited in the Earth and eventually made its way to your wedding band. But it started in a kilonova, and so the kilonova we observed here is now dispersing its gold to make some alien wedding band somewhere in NGC 4993 someday. So actually, they came with the question, okay, how much gold was actually made there? So we can do the calculation. There are different estimates. We're still working on it, but it's about 100 Earth masses of gold are made in 1 kilonova, right? That is a lot. And actually, someone asked, well, how much is that worth? So an ounce of gold is worth about just under $1,300. So if you multiply that by the number of ounces in the Earth mass, you get 25 million dollars. Who said there's no money to be made in astronomy? Right? Now, Business Insider actually published this number. They got a number that was off by a factor of 250, but there's so many zeros that who cares? So now I am an astronomer. I'm not an economist, okay? I'm not an expert on this stuff. But I think, supply and demand, if we did have access to 100 Earth masses of gold, it would be worth exactly $0. So there is no money to be made in astronomy. That is one side of what we learn, where gold comes from. The other side is we were able to actually use this kilonova to measure how fast the universe is expanding, which is a super exciting result that came, one of the 80 papers. You'll recognize us over there. The idea here is we know which galaxy it came from. This galaxy is moving away from us because the universe is expanding. We can measure how fast using our standard techniques of light. But the kilonova, by how strong the gravitational wave signal was detected in LIGO's detectors, we know how far away it is, totally independently. Right? They know how strong a neutron star merger should be, and they know how strong it was when they detected it on August 17th. So you can calculate the distance in a totally independent way of anything we've ever done before. And they can use those two numbers, the distance that they get and how fast it's going away, that we tell it from our optical observations, and deduce a number called the Hubble constant for how fast the universe is expanding. So there have so far been the two main estimates of the Hubble constant. This is the value over here, it's around 70. So one result from the Planck collaboration, of which UCSB is a part of, got this result that's a little under 70. A different collaboration called SHOES uses supernovae, so exploding stars, to measure this out to large distances. They got a number a little above 70. And so we're actually kind of worried about this discrepancy, that these two methods don't line up. So it's great to have a third method. And amazingly, it came right in the middle. This peak here is where they think most likely the Hubble constant is. It's right in between these two measurements with a pretty big error that kind of says, yeah, you could both, we agree with both of you for now. But as we get more and more events, of course, we will be able to maybe solve this mystery of what's the real value and why these two other methods are discrepant. So we learned a lot from this one event. From the level of really nuclear physics, how does atomic nuclei work at those densities and in the process of where gold and other heavy elements are made in the universe? That mystery is solved through the fact that gamma rays are actually made in merging neutron stars, this connection which we had thought only theoretically before, now we know, out to the biggest thing we can imagine: how fast is the universe expanding? So really this one event, from nuclear physics to the universe as a whole, has taught us a lot of things in between. But a few things, a few things are still a mystery. For example, what did these two neutron stars make? So here you see, these are all of the neutron stars we know of, are about 1 or 2 times the mass of the sun. The two neutron stars that merged for this event were pretty typical. Here's all the black holes we know of. They start at about 5. We actually don't really know what happens in between or where the limit is. When does a neutron star become so massive that it collapses to become a black hole? And when you add these two masses together, they merged into something that would either be the most massive neutron star or the least massive black hole, but it's right there in that region where we're not sure what happens. So that's still a question. What did this make? Here are all the black hole mergers that LIGO saw. And there are other questions. So, for example, why was it so bright and blue at the beginning? We were not supposed to be as successful as we were if the theoretical predictions were correct. Why was a gamma ray burst so faint? I told you it was about 100 times fainter than other gamma ray bursts we've seen. And also, how common are these things? Because think about it for a second. This thing happened 130 million years ago. But if it would have happened 2 weeks earlier, Virgo would have been turned off, and we would have not gotten that localization, and we probably would not have found the kilonova. If it had happened 1 week later, all 3 of the detectors turned off because they had planned to turn off at the end of August so that they could do some improvements to the detectors. In fact, we had thought, what's the point? Why are you even going to run together with Virgo for 3 weeks? Just turn off. What's going to happen in 3 weeks? Right? It's a good thing we were wrong, but it does raise a question: were we just super lucky, or are these things 10 times or 100 times more common than we thought? So we'll know when they turn on again, and we can study them again. But I really can't think of a similar situation in science in my lifetime where a single event can produce so many staggering insights about the universe, and at the same time charting the course for a totally new era of astronomy, of merging gravitational waves and light in what we call multi-messenger astronomy for the first time. So this is time to thank the team. As was correctly said before, this is not the work of one person. The team here at Las Cumbres, Sergey, Griffin, Daichi, Andy, Jamie, and Curtis, who are most of which are here, I think. Are you guys here? Can you stand up? Sergey is an undergrad at UCSB who did a summer internship for us and wrote all the software that did everything I told you about. We also have collaborators around the world on this project who helped us come up with this strategy, figure out how we could use Las Cumbres Observatory in the best way to do this. But of course, none of us would have been able to do any of this if it weren't for the staff of the observatory, amazing group of software engineers, hardware engineers, administrators, everything that makes this all happen, including the dogs, who play a vital role in making really this incredible piece of technology work seamlessly. And for this event, other than us not expecting, a gamma ray burst to happen, once we told the telescopes what to do, it was flawless. Andy and I actually went to watch the eclipse 3 days into this thing because we knew the telescopes were just taking care of everything for us. They're robotic. Other groups had to be calling up their friends on the phone. Can you observe this for me? Are you on the telescope? What's the weather like? We just clicked the button and all of this happened for us. And of course, none of this wouldn't happen without the vision of Wayne, who founded Las Cumbres. And really, I was serious that there is no money to be made in astronomy. We don't do it for that. We do it because we're curious about the universe and because we want to know a little bit more than was known yesterday, and because we want to expand the limits of human knowledge about the universe and our place in it. And I don't know anyone who embodies that more than Wayne. So thank you, Wayne, for putting so much effort into this incredible project. So what's next? Well, LIGO and Virgo have turned off. We all had a sigh of relief. Give us just a break here to get ourselves together for the next one. While they're turned off, they're actually making the instruments more sensitive, so they'll be able to see neutron stars mergers further away. And when they turn back on, this thing could happen a few times a year, and when they reach their full sensitivity, it could be as many as 40 events a year, so pretty much every week. So we need to figure out how we're going to deal with that, because we can't not sleep for 2 months every time this happens. In addition, other countries are building their own gravitational wave detectors, most notably Japan and India, and this will allow us to find more events, and the more detectors are running online simultaneously, the better the localization on the sky, and the easier the search will be. And recently, the European Space Agency, together with NASA, have approved a gravitational wave detector in space. So it's going to be 3 different satellites shooting laser beams at each other in this futuristic Michelson interferometer that involves 3 sets of lasers. The idea there is that they can detect gravitational waves at much lower frequencies than we can from the ground, because no one is plowing snow over there, okay? So it's a very isolated, very clean environment, and they will be much more sensitive. So they will be able to detect things that we can't even see with LIGO, like the mergers of white dwarfs, the mergers of supermassive black holes. If you got a bookmark when you came here today, then that bookmark will tell you one of the types of things that this space detector called LISA is going to be able to find. And also, it will be able to see neutron stars mergers years before they merge. So the neat thing is it'll be able to tell us, oh yeah, there's going to be a neutron star merger like the one you saw in August, but it's going to happen right at that position 3 years from now at this time. Okay, so we will definitely be prepared. So there is a lot going to happen, and I'm going to disagree with Wayne that this was the biggest discovery our observatory was involved in. I think there is more yet to come. But either way, I think we're extremely fortunate to be living in a time where these totally new windows on the universe are opening up for us, and we can only imagine what we are going to find next. Thank you very much. So we're going to try and get a few questions in. If you have a question, please raise your hand, and Griffin will head up to you with the microphone. And please wait for the microphone so everyone can hear your question.
In your periodic table, the elements discovered or created by the neutron stars were colored yellow, but you had some of those that were only partially yellow.
Yep.
That means supernovas and other events can make small quantities?
Yeah. So I wouldn't stake my career here on exactly where that yellow ends, because that depends on knowing how much stuff was made in this event, and more hard to know for now is how often these things really happen, right? This one made 100 Earth masses of gold, but if it happens once every 100 years in a galaxy or once every 1,000 years, that changes the overall, how much gold can it provide to this galaxy. So this is the current best estimate, and yes, some of the things actually it made a little bit too much, and so we'll need to see how that works. And some of it probably doesn't make enough, and there are other sources, and supernovae are one of them, as you mentioned, that can make this, but we don't quite know how much. So this will really be something we can probe when we have more events and we know the rates better, and was this a typical yield, or was this, much stronger or weaker than other events? It's still just the first one, but this is definitely one of the questions that will be asked.
One of the things I heard about that this may have also put a nail in is MOND, is modified Newtonian dynamics. And for people who didn't like dark matter were proposing that Einstein wasn't quite right with gravity and that there were other models. And this seems to have put a nail in that.
Okay, that is an interesting aspect that I was not aware of, but it's possible that this could help us constrain dark matter. I'm not sure how. I have not actually heard about that. Right, but how does this put a nail? I know how the kilonova would be relevant to saying whether we're modified Newtonian. Right, okay, yes, that makes sense. So the idea here would be, okay, there's this problem, I don't know if everyone heard about that, about 95% of the universe, we don't really know what it is. Everything we talked about here and everything that makes us is atoms, matter that we understand. Turns out that's just 4% of what's out there. 25% is dark matter, so that's just us saying it's something that does something with gravity, but we don't know what it is. So it is totally possible that gravitational waves and the way they behaved in this event can tell us something about the laws of gravity that maybe were proposed to say there is no dark matter, we just don't understand gravity. But now we understand gravity better, and we can say, no, we still need the dark matter to make it work. But yeah, that's a really interesting, another interesting discovery to come out of it that I haven't been aware of. I'm still making my way down those 80 papers, so it takes time.
Can you help me understand the Hubble constant and what it means, what the implications of it being at 70 are?
Yes. So we observe that all galaxies are moving away from us. We see that because their light gets shifted to the red. That tells us they're moving away. And that is happening because the universe is expanding. The other thing we see is that a galaxy that's twice as far is moving twice as fast away from us. This is very interesting because if you take a picture where everything that's twice as far is moving twice as fast and you rewind it, it all comes back at the same time to the same place. This is actually one of the pieces of evidence for the Big Bang theory. Now, you can still have that relation, but the absolute velocity, you need one velocity to scale it, is different. So, this one could be moving, say, at 10 kilometers per second away, and the other one is moving at 20, or it could be 20 and 40, or it could be 100 and 200. So the Hubble constant is essentially telling you where that number is. So the 70 is actually kilometers per second that a galaxy at 1 megaparsec is moving away from us, which is about 3 million light years. Just that's where they decided to put the scale. So 70 means that if you're looking at a galaxy 3 million light years away, it's moving away from us 70 kilometers a second, and then twice as far is moving away twice as fast, but that gives you the scale. Okay. Any other questions? I guess there's one more down here.
It might seem a very silly question or a very childish one, but I want to know, you said that the neutron stars is where they have the elements shaped. How did gold and so on pop up on Earth?
Yeah, no, that's an excellent question. According to the Big Bang theory, the universe was really made mostly with hydrogen and helium. Then we need stars to make the heavier elements in their cores. They take hydrogen, helium, turn that into carbon, oxygen, up to iron. Beyond iron was really the mystery, and even those elements that are made in a star are ejected by that star through winds, or can escape that star when it explodes as a supernova. But then the heavier elements we now know are made in kilonova, and again, as you saw in some of the simulations, that material just gets flung out into space. So these gold atoms and lead atoms are just flung out into space, and they, they can fly off for millions or billions of years, and then they might coalesce in some cloud with material that was made in a different kilonova later, and these clouds will form the next generation of stars. And these stars are now being formed from material that was created in the previous generation of stars, or kilonovae, and that slowly just enriched the universe. It's a very slow process. It takes a few billion years, but the universe is patient. And these materials just get dispersed into the universe, kind of like, a sprinkler that would turn on every few 100 years in some galaxy, and it will meet some water droplets from a sprinkler that turned on a few times every 100 years in some other part of the galaxy. Those water droplets, or gold atoms, will form the next generation of stars. The material that formed the sun, in fact, most of it formed the sun, but were made of the leftovers of that material that was still orbiting the sun but didn't make it into the sun. So once the sun got hot enough, it turned into a star. All of this leftover material was what made the planets and us. So every atom in our body and every atom on the planet, you can trace back to the material that made the sun and back to the material that came from some supernova or kilonova before. I think there was one more question here, and we'll end it there. So it is a scientific fact. We are all made of star stuff. That is accurate.
You were surprised by how weak the gamma ray burst was. Why don't you just assume we're off the polar axis?
Yeah, that is an excellent idea, and that is in fact the main theory that everyone has said, that it wasn't pointed exactly at us, it was pointed a little bit at an angle, so it was weaker. Turns out that actually also explains why the radios and X-ray took some time to turn on. It works out that way, and it might also explain some of the things we saw in the kilonova. Some other people, though, say you'd have to have been very lucky for that to be the exact angle, but okay, but clearly we were. Or there are other ideas that the jet of material didn't actually break out, but it just got buried in the neutron star, but that was enough to generate energy that made gamma rays a different way. So we actually don't know. There are these two competing theories now. And I'm looking at them very closely because I think one of them would predict that the light we saw, the blue light, should have been much brighter at the beginning and not go up and down. And I think we might be able to shoot down that theory with our data, but we're still looking at it. Okay, thank you all very much for coming.